So in an earlier video, we actually introduced the course and went through the syllabus. In this video, we will start with the following question. Can anyone spot a strange thing about this boat? This picture was taken in 1844 in a port in Europe. And it was actually, if you take a closer look, you can actually see that this boat has both masts and a new technology at the time called the steam engine. And the main reason was that probably people did not trust that new technology to cross the pond, and they wanted definitely to avoid this ship to being sunk for the midway from the Europe to America. We're actually in a very much similar situation with the other new technology called artificial intelligence. Although we have deployed many AI/machine learning systems out there, they are limited to non-mission critical applications. So what are those mission critical applications we're referring to here? Well, our networks, all of our networks, like the grid network, the telecommunication network, all sorts of mission critical infrastructures they have control mechanisms which are still based on the rule-based systems and specifically designed by humans to take care of all possible situations that these infrastructures will actually face. In the vast field of healthcare, doctors are definitely using intelligence systems, the so-called augmented intelligence systems, such as those that are processing X-rays and CAT scans to detect abnormalities. Surgeons are actually using robotic surgical machines in operating theaters. But when life is at stake, there's always a human behind the scenes to monitor and intervene. In robotic systems, perhaps we are seeing the first application of autopilot technology. So here we see a simulated environment of a highway and a robot equipped with quite a bit of sensing and quite advanced perception algorithms that we will come up in detail a bit later, is having a task to maintain some kind of a constant speed of 40-something, 50 miles per hour. And it's sort of moving along in this kind of highway, obviously has to avoid to crash to other agents, also maintain some kind of a helpful, sort of pleasant travel for all the inhabitants of the vehicle. So we have certain kind of constraints of acceleration, deceleration, jerk, and so on. And when it comes to moving in this kind of lane and comes to another vehicle which is actually going slower, it will actually has the logic and the ability to change lanes and very smoothly, and then move back to the center lane, which is also the safest lane in that environment. So this kind of environment is and this kind of ability that we just saw, it kind of gives the impression of an agent that it is actually quite intelligent. However, for all the control tasks we have implemented here, it's worth noting that most of the control tasks are effectively glorified if-then-else statements. If there is no car coming on the left lane, then I will move. Then I'll check again for other conditions. Have I passed through the kind of car and kind of go back to my center lane, and so on. So in these environments, which are pretty much easy, because imagine the difference between a highway driving and an urban driving, we have already deployed AI systems that are responsible for certain controls, but the underlying control logic is still the control logic of an if-then-else statement that we have seen and we had for the so-called expert systems in the 80s. So based on that demo that we actually saw, what we will do next is we actually draw a block diagram that kind of abstracts what we actually see here on this kind of video. And this block diagram will have two components. The main component here is the environment, which we are not going to be dissecting other than claiming that the environment contains a state, and the state is definitely not known to us. So imagine, for example, as you are driving, at what kind of sort of a state do you have a visibility of what happens to 20 cars ahead of you? Obviously not. So it's the only thing that you know is some form of a partial state, the so-called partial observed environments. Nevertheless, the environment will encapsulate its global state, and some portion of that could potentially be retrievable via the so-called sensors. These sensors are potentially cameras. We have plenty of cameras in this kind of robots with ego motion. We have, let's say, radars. Let me call this as a symbol, and we have also lidars. Let me call this radars with this symbol. Okay, and so all of these kind of sensors are kind of in many instances fused together. We will not be dealing with all the details in this course, but they are what is happening is at the output of this kind of fusion, we are going to be processing all this kind of sensing data. This symbol that we'll be using here is X, and we'll put an underbar under it in order for us to designate that this X is a highly dimensional quantity in general. We'll discuss about dimensionality in a moment. And the first subsystem that we will be dealing in this course is called the perception. The perception subsystem. And this perception subsystem will take this X and will produce a quantity that we'll be calling from now on Y hat. Y hat in general is also going to be multidimensional, but we'll start with a simple use case where it is actually a scalar a bit later in another video. Now, for example, to give you an idea about the types of X's that we are going to be observing, we can, for example, observe video streams as transmitted by these cameras. We have typically around 8 cameras in every self-driving car. So we have some image which has width of W pixels and some height of H pixels. And since every pixel is independent of each other, and they are assessing kind of different parts of the image, then we have effectively what we'll be calling from now on N is the number of dimensions of X. So we can actually see that designation-wise, notation-wise, it will be X belongs to R to the power of N. That's what it means. X is let's call it a vector of N dimensions, and these N dimensions will be in, for the case of a single frame over here, will be W times H, as every pixel is independent of each other. So W times H dimensions. Some pretty large dimensions are present already just from the single image kind of perspective. And we will see now that, and also I can write this as, let's say, a vector from x1 to xn. So for example, n, you can imagine typically, let's say that W is 640 pixels, just 640 pixels, and H is another 640 pixels. So you can imagine that N could be in the many thousands. And what will be the Y hat? Well, let's imagine that this pixel over here, this picture over here has taken a shot of, let's say, a pedestrian. And our task is a simple classification task where we have as one, the pedestrian being present in that kind of scene, or R0, the pedestrian is not present. Let me just draw a dog or whatever in the scene. So In this specific case, our y hat will be a discrete random variable that predicts whether the pedestrian is present or not. So that will be the simplest case of a y hat that we'll come across. Now, perception systems are very heavy in kind of deep learning technology. There's lots of complexity in there, and I will spend considerable time trying to get all the networking and deep networking kind of understood. But they are the so-called, they have a problem, and they are typically kind of fairly reflexive. So reflexive is a term that we actually use to probably you sort of have experienced some kind of reflex, such as sneezing, and obviously you did. But in a fashion over here, in this perception subsystem fashion over here, reflexive means that in one frame we can observe this kind of pedestrian, but in a subsequent kind of frame, let's say a random lighting condition changes. Light is a very heavy determinant of performance of computer vision systems. We don't, despite the fact that the pedestrian is actually there and hasn't really moved from 1 millisecond to the next. So what we will need to employ is what we call the probabilistic reasoning over time. Probabilistic reasoning over time, also known as tracking. So with this kind of systems, what we do is we process these frames in sequence as they're coming out of this perception subsystem, and we are correcting, tracking, if you like, the objects, and then we're correcting from this kind of reflexive or spurious type of errors they are actually making. So the ability for us to track is fairly pronounced if you think about our ability to fill the gaps. So for example, if you can imagine that I'm rotating myself, let's say 360 degrees, you can actually, or better, go behind an occlusion temporarily. You can actually infer that I'm actually behind that kind of occlusion. And therefore, our ability to just look at these systems, this system is built in our kind of brains on how we actually track objects and how we actually fill the gaps. It's not only perception that we fill the gaps. We use this in perception kind of problems. We use this kind of probabilistic reasoning over time. We also use it in language. So as I'm actually writing over here, sometimes my writing is not really high quality. So you can, if I omit a sentence or a word, you can sort of fill the gaps for that specific word, and you can infer what I was trying to say there. Okay, so the next step downwards is down this kind of a chain is what we call now logical reasoning. So logical reasoning is typically assisted by what we call here the knowledge base. And we'll see some examples of all that in a moment. And we receive this kind of y tilde over here, the so-called corrected kind of prediction. And what we actually can do in this probabilistic reasoning over time, together in combination with kind of logical reasoning, is to create symbolic abstractions. So symbolic abstractions can work in combination with neural networks, the so-called neurosymbolic systems, to create symbolic representations of our world and greatly accelerate inference time, or can actually help us to do inference even in the absence of any sensing information. So we'll see that in a moment how this is could potentially be done as we're discussing the various ways that we actually can implement AI. And the fourth subsystem is the so-called planning. And in this box over here, I forgot to mention, is called knowledge base. And it acts as a kind of a database of all of our knowledge at this moment in time. That includes percepts, any logical reasoning that we have done in terms of inference, rules of the world, and so many others. So planning is the next subsystem down, and in the planning, obviously, we have determined, now we have a task to solve, and we have, let's say, to go from place A to place B. Obviously, everyone has used Google Maps as driving directions. So everyone actually has used a planning system where Google Maps is, let's say, planning a route for you. And at any moment in time, depending, let's say, of traffic conditions, it will also be able to replan. And so planning is, in this case, happens with some kind of interaction, but in many problems, we are dealing with planning that without really interacting with the environment. So if I distinguish planning without and with interactions, the one that with interactions, it can potentially, it can be called reinforcement learning. Reinforcement learning. So we'll see how reinforcement learning is implemented. And in this reinforcement learning, we have definitely communication with the environment. And in fact, this communication is in many senses one way from the environment to us. And this R over here is called reward. And of course, we need to design, if you like, a reward function inside our agent in order to sort of receive the right reward at that right moment to lead us to the optimal sort of trajectory, such as in robotic applications in many instances. So we'll see that also how this is functioning in a moment. All right, so and then finally, we have a plan, and the last kind of block over here is called a controller. And the job of the controller is knowing exactly all the details of the robot. In this case, all the actuator details, what kind of individual component controllers has wheels, it has propeller, whatever depends on the robot, it executes the plan. And effectively takes actions. In our specific example, we saw the actions where, for example, the steering angle theta and some form of acceleration, deceleration A. So in general, this will be the actions. And what happens now, another cycle is going to be repeated. When the robot is taking action, the state of the environment is changed. Let's say the robot moved by a certain kind of distance. This changed the state of the environment. This leads to new information about that kind of state coming in our agent. And all these kind of subsequent kind of blocks are going to be executed over and over again until the environment kind of terminates when we reach our destination, or whatever the task we have, the plan we have is fully executed. So the second system that I would like to show you is kind of considered to be a bit more evolved than the previous Egomotion kind of AI agent. We still see a robot moving in a kind of a closed world. The pictures is pixelated in this case because we have shot this kind of video at the sort of output of that kind of sensor, and this actually sensor is we are downsampling quite considerably from the camera to produce an input in this kind of neural network. Neural networks are not known to require 4K video in order for them to perform well. And also computationally, this is actually going to be a very heavy sort of a load for the neural network to do so. So the role of this kind of agent is to move around in this closed environment without really crashing. But the architecture inside it is a bit different than the one that we have seen earlier. So instead of me drawing all over this kind of block diagram again, what I'm going to draw here is only the agent kind of a block diagram from left to right. So the whole agent is quite considerable neural network. So this is a deep network that accepts the raw information or the sensing information, the X underbar that we have seen earlier, and directly spits out the steering direction and the acceleration deceleration alpha. So now we have an end-to-end system that is doing all the tasks that the previous subsystems, the individual subsystems were actually doing, including perception, probabilistic reasoning over time, control, and so on, planning, and so on. So this is a second kind of system that we can actually have. This is called, let's say, imitation learning. We have plenty of learning approaches and on how we actually can train this kind of neural networks and these robots to behave the way we want. But in this kind of imitation learning, what we actually have done is we have gotten kind of training data which are a bit different than the training data we were acquiring from the earliest system. Here we have actually used humans in the loop to drive humans in the loop. They drive the robot in exactly the same environment. That's kind of important. And therefore, we actually can pick up their own steering directions and accelerations, decelerations, and couple them with. So this is now my the Y hat, and our training data were effectively the combinations of images and the Y's, which are the vector theta and A. So these were basically the types of data we have to accumulate. We have to accumulate mountains of this kind of data, not only data that describe the sort of how well the driver that is performing well in around this kind of environment, but also gather data of corrections. And this actually was deemed to be very important for training, if you like, an agent that will be able to not only behave well in but also to be able to correct any mistakes that they were making. Okay, so that's the second kind of subsystem that we have sort of thought to present, and these kind of humans in the loop are increasingly kind of present in many AI systems. We have seen it even recently with large language models and how we can get them to behave and perform much better than without any human feedback. So a final video on the what could potentially be the case in robotics in a few years' time. This is in the lab, obviously, and obviously there is a behind the scenes with a big red button ready to press to press it the moment something goes wrong.